In this video, we will discuss one of the numericals from the gas turbines. So the question is as follows. Find the required air-fuel ratio in the gas turbine whose turbine and compressor efficiencies are 85% and 80% respectively. Maximum cycle temperature is 875 degrees Celsius and the working fluid can be taken as air, which enters the compressor at 1 bar and 27 degrees Celsius. The pressure ratio is 4 and the calorific value of fuel is 42,000 kilojoules per kg. There is a loss of 10% of the calorific value in the combustion chamber. So now in this question we have to take the gas turbine which is having an actual process. Actual and ideal are the two processes as shown in the TS diagram over here. So 1 to 2 is the ideal compression in the compressor and 3 4 is the ideal expansion in the turbine, but 1 to 2 dash and 3 to 4 dash are the actual processes, and we are taking the actual processes in this question because the turbine and compressor efficiencies are given. When these efficiencies will not be given, then we will not consider this 2 dash and 4 dash. We will take 1 2 3 4 will be the ideal cycle and calculations will be based on the ideal cycle. But in this question we will move on with the actual cycle. Now maximum cycle temperature. The cycle temperature is maximum at 0.3 because after the compression naturally the temperature will increase, but when we add more heat during the process 2 to 3, the highest temperature will be obtained after heat addition. Rest of the points are after losing this energy, so the temperature will be reduced, and hence and thereafter after the extraction of heat the temperature will be still reduced. So the highest temperature is at 0.3 and in most of the questions this is given, so the maximum cycle temperature will be at 0.3. So what else is given? The working fluid can be taken as air. We'll always take air as the working fluid of the gas turbine because only then we'll be able to use the ideal gas laws, the values for the Cp, Cv and gamma for air only. Now the compressor, the air enters the compressor at 1 bar and 27 degrees Celsius. So as we know that 1 to 2 is the process in the compressor, so compressor entry is at 0.1 and hence the condition at 1 is 1 bar and 27 degrees Celsius. So I have taken T1 as 27 degrees Celsius, which will be equal to 300 Kelvin, P1 as 1 bar, then T3 is 875 degrees Celsius, which becomes 1148 Kelvin. Then Cv, calorific value of fuel, is given as 42,000 kilojoules per kg. The pressure ratio is given as 4, so Rp I have taken 4. Eta C is the efficiency of the compressor 0.8 and efficiency of the turbine 0.85. They are also given. So for solving this question we will use a relation that we have already used in the derivation of Otto diesel dual cycles and in the Brayton cycles, cycle 2. So now T2 by T1 is equal to P2 by P1 raised to the power gamma minus 1 upon gamma for an isentropic process. So I am applying this for a process 1 to 2. So in this particular formula we know that P2 by P1 is the pressure ratio only. In a gas turbine cycle we have already defined the pressure ratio initially, and that is equal to the higher pressure upon lower pressure. So higher pressure is this pressure line and lower pressure is this pressure line. So P2 by P1 is equal to P3 by P4 will be known as the pressure ratio. So here we will put P2 by P1 is equal to 4 because pressure ratio is given. Gamma is equal to 1.4 for air. This you should remember. Then T2 is not known, that we have to find, and T1 is equal to 300 Kelvin, that is this is given in the question. So we will obtain T2 using this formula. Now as we know that the compressor efficiency is given in the question, and the compressor efficiency we have defined it in another video and we have given it in terms of the ideal and actual conditions as T2 minus T1 upon T2 dash minus T1, and we have put it equal to 0.8 as it is already given. So by this we know T1, we know T2, we have already calculated T2 here, we know the compressor efficiencies. The only thing which is left is T2 dash, so we will get the T2 dash from here. Now applying a similar methodology for the process 3 to 4 and further for 4 dash, we apply the same formula. T3 by T4 is equal to P3 by P4 raised to the power gamma minus 1 upon gamma. Putting the pressure ratio is equal to 4, gamma is equal to 1.4, we get T4 is equal to this, and then we are applying the formula for turbine efficiency, which is actual upon ideal temperature differences. So actual is T3 minus T4 dash and ideal is T3 minus T4, where we know T3, which is given in the question, we know eta T, and we know T4 as we have calculated it here only. So T4 dash will be calculated from here and it will be 828.87 Kelvin. So by this we calculate all the conditions at all the points, all the salient points of the cycle. Conditions are not now known. So 1, 2, 3, 4, 2 dash, 4 dash, all conditions are known in terms of pressure and temperature now. So if the question says find the pressure and temperature at all the salient points of the gas turbine, so that is done. This may be a question sometimes. Now next is, one can ask for the compressor work, turbine work, ideal one or actual one. I have also included them in this particular question, although they are not asked in the question only, but I have added them for the sake of learning. So ideal work output from the turbine. So ideal process is 3 to 4. So it will be Cp T3 minus T4. So it is Cp T3 minus T4 and it will be in per kg, because right now the mass flow rate is not given in the question. If it will be given, then it will be mCp dt. Here we are calculating it for 1 kg. Now actual work output from the turbine will be 3 minus 4 dash. So this will be Cp into T3 minus T4 dash, and again for per unit mass we are obtaining the actual work output. Ideal work input into the compressor will be Cp T2 minus T1 and actual will be Cp T2 dash minus T1, and I have calculated these as follows, and these are also in specific terms or per unit mass terms. Now the efficiency of the gas turbine cycle or the thermal efficiency of the cycle has we have the formula for it. We have derived in the derivation in another video. So 1 minus 1 upon Rp raised to the power gamma minus 1 upon gamma, where Rp is the pressure ratio that we have already, that was given in the question only, and we can have it if we know the two pressures of the cycle. Then gamma is 1.4 for air, so we get the efficiency by putting the two values as 32.7%. Now this is also not asked in the question, but I have added for the sake of learning only. Now I will move on to the part which is being asked in the question, which is the air fuel ratio in the gas turbine, which is working with these conditions. So for that I am following some steps which are needed. So first we are calculating the heat input. So heat input will be from till the point 3, because this 2 3 is the heat exchange process, heat addition process at constant pressure. So till point 3 we have to add heat, but usually it starts from point 2. But when the compressor is having an actual process till 2 dash and the air is heated till the point 2 dash in the compressor only, hence we need to supply the heat from 2 dash to 3 only. So the heat addition will become Cp T3 minus T2 dash. So this is what I have written. So mCp dt is the formula generally, but m is 1 as we have taken it 1 because it is not given in the question. So Cp dt will be T3 minus T2 dash as it is the actual condition. So we get heat supplied as 669.09 kilojoules per kg. Now as we are given with the calorific value of fuel as 42,000 kilojoules per kg, but another thing which is given is that in the combustion chamber, this one, loss of 10% of the calorific value takes place. That means 10% of the heat is lost and rest of the 90% is obtained. So actual heat which will be obtained from 1 kg of fuel will be 90% of the total. So that means 0.9 into the calorific value, or it is 37,800 kilojoules per kg. So now for calculating the air fuel ratio, we apply the unitary method. This is the most simple way. I am explaining in it like you are in class 9th. So 37,800 kilojoules heat is supplied by 1 kg of fuel, because it was the calorific value and 10% of it is lost, rest of the 90% will be supplied to the air for heating. Now if this is supplied by 1 kg of fuel, so 1 kilojoule of heat will be supplied by 1 upon 37,800 kg of fuel. And if we need 669.09 kilojoules of heat, which is required for 1 kg air heating will be 1 upon 37,800 into 669.09 kg of fuel, and we get it as 0.01770,793. I have taken very much number of decimal places for the best accurate results, but you can take it up to the 0.0177 kg of fuel. So the air fuel ratio can be written as, now as we know that for 1 kg of air this much heat was required, so 1 kg of air needs this much of fuel, so 1 is to the fuel amount is the air fuel ratio, and we can also divide this do the reciprocal of this, and then we can have the air fuel ratio as 56.495 is to 1. So this is the air fuel ratio, and like this we can have the air fuel ratio, and we can also calculate the conditions of temperature and pressure at all the salient points, the turbine work, the compressor work, net work, specific work ratio, back work ratio. We can have all from the temperatures at the all the points of this cycle. So this is the one of the numericals. I'll discuss another numerical in another video of this gas turbines. Thank you so much.